I make it real? That is to say, there are all these concepts, there's all these mental models that I learn when I'm learning Python. And as an expert Python user, how do I go back to those basics and discover what's lurking behind these mental models, these concepts, what decisions I might be able to make in my code, and what those decisions actually mean, what the implications of them are? Well, in today's session, we are going to talk about some mechanics that you may have encountered when writing Python code and dig into them deeper to understand what are the real consequences of all of the choices that we make. Good morning, everybody. My name is James Powell, and I will be the lead presenter for today's session. I am joined today by my colleague Cameron Riddell, who will be watching for questions as they come up in Discord. And so, as we go through all of the topics that we have set in front of us this morning, I strongly encourage you to take a look at joining our Discord channel if you haven't already, and putting questions as they may come up. Now, for those of you who are watching this session afterwards on video, don't worry, you can always send us an email, or you can always join our Discord server and post questions about this session there. And the questions that we'd love for you to post are questions like, well, there's this one little corner case. Is there maybe some catch to what you're showing? Is there maybe some case under which what you're saying doesn't really work out, or some additional qualification? Or even questions like, well, in my code, I ran into something that looked like this, and I think this applies to what you said here, or at least I think what you said here applies to the problem that I have in front of me. How can I use that to improve the design of my code? Whatever the case may be, we strongly encourage you. Please send us your questions, and we'd love to show you how everything that we discuss in this session and in others can directly lead to you writing better code. With that said, I want to jump right in to our first of 4 questions about Python. We're going to talk about the difference between objects and closures, objects and generator coroutines. We're going to talk about the difference between inheritance and composition. We're going to talk about why we use object orientation in the first place, and we're going to talk about boilerplate elimination tools. And so, to get us started, I'll share my screen with you. What is the difference between an object and a closure, or an object and a generator coroutine? And how does this affect how I might design my code? How does this affect the usability of the APIs that I might provide? Let's look into this. Well, we know that in Python, we have first-class functions. And when we say first-class function, what we mean is a function can be treated like any other data, like a string, like a list, like a numeric value, which means we can do things like put functions into data structures. Here you can see this loop is looping over the function f and the function g, and it's invoking them. And this is materially different than if we were to perform the invocation here in the loop header. Simply because if one of these invocations happens to be very slow, and if it happens to be the case that we aren't necessarily going to go through every pass of this loop, for example, there may be a break here. Well, in this case, we're deferring the invocation until the body of the loop, which means if we were to break out of the loop early, well, we wouldn't perform operations that we didn't care about, that we never would visit. Whereas here, we might have to pay the cost of all of the invocations up front, and then if we broke out early, well, then this is just some kind of loop control, but it's not going to save us from doing additional redundant computations. In fact, we can make use of first-class functions to accomplish a lot of things that otherwise would require a lot of code in other programming languages. First-class functions is, in fact, one of the reasons why originally people really liked Python over programming languages like Java, where there needed to be a lot of additional patterns and additional superstructure on top of your code to accomplish things that can be done very readily, very easily with just first-class functions. Note that in Python, we can also dynamically define new functions at runtime. And so in this block of code, the function g is being defined not when this code is parsed and compiled, but when this code is actually run. And so this line of code here says, go and actually create g for me, make it available for my use, and then invoke it. In fact, when we think about things like lambdas, we can think that often the case when we have a lambda is that this is either being returned or this is being put into a data structure, and the lambda really shows up as some piece of data here. Here you can see we have a list of 2 functions, 2 lambdas, or some return value that is being dynamically created. Here we're returning a brand new function. In fact, when we think about how things like instance methods may work, behind the scenes, those instance methods may actually be dynamically creating bound methods bound to the self parameter, and the underlying code may look not too dissimilar from this, although of course it may be occurring at the C level rather than at the Python level. Note that when we define functions dynamically, we are genuinely creating a new instance of that function. And so in this example, where we have called f twice, which has then created g twice, the two g functions that were created here are not the same g function. That is to say, they do the same thing, they take the same arguments, they return the same value, but the actual underlying function objects are distinct. If we take a look at these and we ask them, is G0, G1, are they the same function object? Well, the answer is no. And this would be different than if, for example, we were to write some code like this, in which case G0 and G1 are the same function object. In other programming languages which have mechanisms that take what look like nested function definitions or embedded function definitions and lift them up to some higher level, well, it may appear that we're doing what Python's doing, but what we'll see is that the function that's actually returned in both cases is in fact the same underlying function, which is not the behavior that we see here. Now do note that when we say is it the same function or not, well, that's a little bit of a loosey-goosey question in Python. And the reason for that is, are these two things the same function? I mean, they do the same thing. They have the same signature. They even have the same docstring. They only differ in that they are distinct function objects and they have different names. And Python really has no way to determine if these two functions are equivalent or not. There's a good reason for that. One of these functions might be written in C and the other function might be written in Python. So we can't just say, oh, do they have the same bytecode? Well, one of them might not have bytecode at all. Also, a question of are we considering the name, are we considering the docstring, might clutter up this analysis. There really isn't one very good way for us to do this. We can, of course, ask the more precise question, do these functions have the same name? Although that's maybe not that useful of a question. And we could even say, okay, go into the code object for these functions and see, do they have the same code object? No, they don't. But do they have the same bytecode? Well, it should be the case that the bytecodes are equivalent. And so if the signatures are equivalent and the bytecodes are equivalent, then to a certain degree we can say at least they do the same thing. Note that if we take the dynamic function creation example and we take the resulting function and put it into a set, well, here, if we're looping 3 times, we will see 3 distinct instances of this function, which is why if the code were just the following, this code is ultimately quite meaningless. It created a function, it threw that away, created a function, threw that away, created a function, and kept that. And unless we're storing each one of these invocations of this function, well, I don't know why we wanted to create this function 3 times and then throw away the first 2 times we created it. Now, of course, this would be different if we immediately used the function, or, of course, if we stored this function into some structure. The double equals check on a function is just checking to see if the 2 function objects are identical. It really is just decaying to an ID check, and that's about it. We actually have to explicitly dig through this function object to see if they're equivalent, of course, by looking at things like the code, co-code, or maybe even the name if that's something that's meaningful to us. Now, when we define a function dynamically, well, Python looks at the function name, it looks at the function docstring, it looks at the body of that function, and it creates a function object for us. And the function object consists of a couple of different pieces. Of course, the name, the docstring, the code object. It also consists of information regarding the default values and the closure. And so here we can see, well, the name of f is f. We can see what the docstring of this is. We can see the code object that was created. We can even see the default values that are available for the parameters for f, for x's and y's. And we can see the closure, although the closure doesn't seem to be populated just yet. If we take a look at the code co-code, here we can see the bytecode that was created for this. This is not particularly readable. In fact, probably we want to use the dis module to interpret what that bytecode is, and you can see here, well, quite a lot of bytecode for such a simple function. But these are all the pieces that are created. And this is why, for example, if the default arguments for a function are mutable, Well, those default arguments are not populated on every invocation of that function. They're populated on the function definition. This is what people call the mutable default arguments problem. I want to use the word problem very lightly because this is really just a direct consequence of the design of how functions are dynamically created. It's not necessarily something that is a mistake in the design of Python, although it may lead to code that is a little bit confusing for people who assume that every time we invoke f, we're creating the list 1, 2, 3, 4, 5, 6 anew. That's not what we're doing. In fact, every time we call f, we're just reusing the same default value that we specified when we first defined this function. So if we look at these defaults, we'll see that it's capturing a reference to a single list, 1, 2, 3, 4, 5, 6, that it's then reusing, and thus mutations to this default argument will persist across function invocations. Is this a problem? I don't know. This is kind of like static at function level in C, so you could use this for something maybe that you might want to do. I don't know that anybody really uses this to accomplish any goal, but it's just a direct consequence of the design of how functions are created in Python, and so I'd hesitate to call this a problem. I would say maybe it's merely a source of confusion. Now, when the bytecode is created for a Python function, well, we have to do a couple of things. One of those things is scope determination. We have to determine anytime we see a variable access, a loading or a storing, a getting or a setting for some variable, where did that variable come from? Was that a local variable? Was that a global variable? Or was it something else? In the case of this function here, we can see that it refers to x that was not defined anywhere in the body of f and wasn't passed into f. So this ought to be a global variable. And that's exactly what the bytecode tells us. Python says, when you're going to read x, load it from the global scope. In this case, it's very clear that x is a local variable. And of course, if x were brought into scope like this, then it would still be a local variable. You can see the load fast remains. If x were brought into scope via this mechanism, you can see it's still a local variable. You still see that load fast. In fact, there are a finite number of static forms that can create a name binding in Python, and Python's parser just looks for those forms and uses them to determine, is this a variable that was brought into existence in the body of this function, or is this a variable that might have been brought into existence outside of this function? This is how we determine whether it's local or global. Now, if the name binding was brought into existence outside of the function, but inside the enclosing environment, so not global and not local, but something looks like this, a function which defines a function where this variable was passed into this outermost function. This is our third most important scope. This is our closure scope, what we might call a load deref in Python. And this is statically determined by the Python parser. This is why if I were to do something like this in my code, this code would erroneously create a load fast instruction because it would say, oh, x equals something. This must be a local variable. And if I were to say x equals x plus 1, it would say, well, same thing. That's a local variable that we're just incrementing. Which means if I were to say x plus equals 1, my Python parser would erroneously say, oh, x is a local variable that we're incrementing, even though it's from the closure scope. Which is why I may need to hint to the parser, no, you're going to get this wrong. You're going to assume this is a local variable, but in fact it is a closed over variable. You need to generate a load deref bytecode. And in fact, the global and load deref keywords in Python, all they do is hint at the parser. You're going to guess wrong for where this variable comes from. Here's where it actually comes from, either the global scope or the dereference the closure scope. Note that there's no local keyword here. You can't tell it, oh, you're going to guess wrong. You're going to think it's not local, but it actually is local because we have a strict number of set static forms that can create a local variable. And Python says, look, I don't need help identifying those. I already knows what those are, which is also why certain things like this won't work. Here, it may be the case that, oh, we're creating a local variable by writing into the locals dictionary. Well, we're going to see an error here because this is going to generate it's going to generate a load fast bytecode here. So the reason this is going to generate this is because of this line. If I remove this line, you'll see it's going to generate a load global because it can't quite see through that arbitrarily complex computation, because you could think this could be anything. This could be, else something like that. And Python parser can't statically determine that x is a local variable here, and so it's going to erroneously assume that it's a global variable. And this might be maybe the case where you might want to do something like local x, but it doesn't exist, and you're not really supposed to do this anyway. And so let's rewind this to a version of code that actually makes sense. Here we go.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.